E shikoni dot ekranin? Ekranin e shikoni dot?
Jo, profesor, jo nuk e ke bërë prezent.
Okay. Okay, po. Për shembull, mund të konsiderojmë një shembull, për shembull kemi when A is equal to, let's assume that we have a tunnel and this tunnel is a tunnel that connects, let's say, two cities, and we say that it's a tunnel only because the units of these quantities, they will be in meters. So far, we've considered distances, at least in the order of centimeters. They were more or less what they were. So here, if we have A, which is meter, B is also meters, and the question is the following. For example, let's try to identify what is the cutoff frequency. So as we denote this one as Fc as a function of m and as a function of n. So and here, okay. So now regarding the cutoff frequency, we have the expression which is given by, wait a second. Let's see whether we get. So the cutoff frequency, we have an expression of Fc as a function of Mn. This is equal to, so this would be units of 1 over the second. And here in the square root, we have m pi over A all square plus m pi over B all square. So, wait a second. Okay, this, sorry, okay. So this is the expression for the cutoff frequency. What other terms do we need here? So this is 1 over A, and this is 1 over meters. Is it correct? 1 over A, yeah. And now here we should get the unit of 1 over seconds. So what other units do we need here? Any idea? So actually, if you pin at the camera, I think you can see this, right? So can you help me here? So what is the cutoff frequency as a function of m and n? So here the unit is 1 over seconds. The unit of this term, because m is a number, no unit, pi is just pi, it's also a number. A is measured in meters, so we have 1 over A, 1 over meter squared, square root is 1 over meter. But we have an equation which the units in these two sections, after they are multiplied, we should get 1 over second. So apparently, it is good if we multiply this side by the term, which is a unit of meter per second. Now, what does this term include here? So here we can include the c divided by 2 pi. Is this expression correct? Can you check this? Any comment? Është shpreha saktë?
Po, profesor, saktë është.
Okay, so first of all, we check the units, and the units look good, but we can also simplify this a little further, because we can factor out the pi, so this is pi squared, or we can do it like this. So we can get c over 2 times 1 over pi squared, m over a whole square pi squared plus n 1 over pi square m divided by b square pi square root. So the pi's, they will cancel out, and we get a simpler expression, which is now, we just substitute for m and n, and now this equation will be written, so we are assuming that this tunnel is filled of air, so assuming that here we have vehicles passing, so nothing scary should be involved, no extra materials, and now the cutoff frequency will be equal to, now let's, so what are the relevant numbers that we need? We need the speed of light, which is c, and this is equal to 3 times 10 to the power 8. Okay, so this is the speed of the speed of electromagnetic waves, end of light, of course. And here we write that this. Okay, we need here to put variables as m of m and n, and then we have the expression here, which is the cutoff frequency, is equal to c over 2 times the square root of m over a all squared and n over a. Okay, so here we have m and n. So apparently we're going to pick up the initial modes is going to be 0, 1, and 1, 0. Let's work with these. 1, 0, 0, 1, and then we have 1, 1. Then we have 1, sorry, this is 1, 2, 3, 4, 5, 6. Then we can put 2, 2, 1, we don't have it yet, 2, 1, then we have 2, 2. Let's see if we can do this one like this. Then we have this. Okay, we got quite a few modes, and let's see that here this cutoff frequency is equal to c divided by 2, and c, this is equal to 3 times 10 to the power 8 divided by 2 times the square root of m squared over a squared. So m squared is going to be d2. So here times d2 divided by a squared divided by a1. So we keep this value $a1 divided by okay, this is m squared over a squared plus n squared over b squared plus n squared is e2 times e2 divided by b2. Oh, this is wrong actually. It's not a1. It should be a2. So this is gonna be b2. So we want to divide square by the 4.9 squared divided by $b$2 divided by $b$2, because we want to keep this value as constant, and we get a 0 because this is not a1, this should be a2. So to keep constant the value of the column, we put a dollar. To keep constant also the value of the row, we put another dollar sign. So apparently we get here, and let's divide this whole expression. Let's divide this one by 1 times e to the power 9. So is this correct? Wait a second, try to divide this one by e to the power 9. Okay. What we get here, it is, yeah, it might be correct. So then this is, if we multiply this by 1000, this is 8 megahertz. If I'm not wrong, let me check the numbers. Yes, this is 8.8 megahertz. And I think we are good. So, okay. So we have expressed this one in gigahertz. So this is gigahertz. This is the unit. And then we just need to calculate all the possible modes we obtain. So it looks like we have all of these modes, which, or we have all of these cutoff frequency modes for this specific mode. So this is TE 10, 01, 11, 12, 13, 14, 15, 16. Again, we have no issue here. Apparently, now we have to combine, let's say here we have the 3, and actually we can also check the following. So 2, 1, and 1, 2. So this is 1, 2, and this is 2, 1. We notice that they are not the same, and this is expected because A and B are different. Okay, so these modes are not degenerate. Degenerate would be two different modes. They have the same cutoff frequency. So these are not degenerate modes. This is not the case. Okay, but now this is. It looks like if we draw a graph of all of these cutoff frequencies as a function of the increasing frequency, we might observe, or we can figure out which modes generates next in an increasing order. Okay, so the reason that we might need to have this is that wait a second. So sometimes I don't know which way we can do this faster. Octal combine. This is something I often use because the graphing capabilities of XZ. Maybe I don't know how to use XZ very well, but we might need to use these values very soon. So these are the different specific modes. And now let's make, so 3, 1, we don't have it. So then let's pick up this term here. Include also the 8. Then this is going to be the 3. And here we get 4. Okay, so here we observe several modes, but let's see now. We have to cut. We have expressed these frequencies in terms of the. Well, this is gigahertz. If we use, let's use megahertz because this would be more visible. So if these are, wait a second. Oh, okay. So this expression is equal to this. If we want to turn this in megahertz, we have to multiply by 1000. So from giga, okay, we get 8.8. And this is what we observe as a, okay, these are the cutoff frequencies of the electromagnetic wave in a tunnel with parameters of 17 meters and 4.9 meters. So these are the parameters of the tunnel. And now a question that we can consider is the following: find the lowest mode that don't propagate. Let's say at wait a second. The lowest order modes that don't propagate at 80 megahertz. So let's say we have 80 megahertz. And which modes can propagate in this range? So if we look here, so we are saying which which modes of the 80 don't propagate. So if we have 80 megahertz and we look at the mode 1001, the cutoff frequency, it is 8.8 and 30. Okay, so these are good. So it looks like we can put, or let's put here, 80 megahertz, and then we can, so this is, and let's consider also the 100 megahertz, and then we have to consider, so this frequency, does it create the 1001 modes? Yes, because the cutoff frequency is 8.8 and 30, so they are good to go. So we can give, so to say, a green light, okay? Then it goes on again, but this one, this mode, the 1.3 mode at 80 megahertz, this one cannot propagate. It cannot be created, okay? So, or it simply it will not propagate because the boundary conditions will not allow that. And then if we look again, it looks like we get a green light for these two here. Okay, we are talking about 80, so we get two more here. And wait a second, so we get two more here. Because these are smaller than 80. Actually, we can write down a code. So, but I'm not sure how to write this one in Excel. I used to know this, but right now I don't remember. There is conditional. You can set conditional. Wait a second. This is review. Conditional formatting. Less than. That are less than 80. Light red field. Okay, I think, do we have any other? No, yellow, yeah, green. Yeah, we did it. So apparently, these, the modes which can be allowed to propagate for an input wave of 80 megahertz, so if we have an antenna which generates this frequency, apparently these numbers in green, these modes can propagate. So we have 10, 1211, then we have 2122. Maybe we should be able to write them in a more elegant way, in an increasing order. But what is the smallest mode? So let's ask, what is the lowest order mode that does not propagate at 80? Okay, this is a good question, for example. So so this one it doesn't, but this is not the lowest order mode which does not propagate at 80, because we should be looking for numbers which are closest to 80, or we have to find the numbers which are larger than 80, but that have the smallest difference with respect to 80. So actually, when we look at these, 92 megahertz, it looks like a good candidate. Do we have 93? We can still get 92. 98, so it looks 92, it could be the answer then. Okay, most probably. So this is the lowest order mode, the 1.3, which does not propagate at 80 megahertz. Okay, so lowest not allowed is 90, it's 1.3. Let's write it like this, the mode 1.3. Oh. So one way to write, so the mode 1.3 cannot propagate at if the original wave is 80 megahertz. Okay, we found, let's see. Okay, then we can also ask a similar question for other frequencies, and okay, so we figure out these were the allowed ones. Actually, let's think if we can come up with similar modes. No, 5 1 1 5. Actually, if we have here 5 1, if we have a look here, this is line 22. So this is 1 2 up to 5, 1 2 up to 5, 1 2 up to 4, 1 2 up to 3, 1 2, of course 2 2 are fine, 1 2. So anything which has one index 1 2 up to 5 is allowed. But 1 3, this is stopped. Okay, so 1 4, it is increasing too fast. So it looks like we understood the order of the modes which can propagate at this specific frequency. Now we can also so this was regarding the lowest mode. Actually, let's write the value here. This is 92.3. 92.3 megahertz is the lowest mode that cannot propagate. Good. So now let's have, actually we can have also 92222. So here we can have 1 2 3 7. Okay, and then we can also have 1 2 3 4 8 9. Base again. Base again. Okay. So if we go down to 9, this is all 2. Then here we have 3. Then we get the 4. And we get the 5. Okay, so here we have other modes, and now let's conditionally check the conditional formatting. So we want to less than 100. So less than 100, which are the allowed ones, and oh, wait a second. Maybe we have also a double condition, so we want to do them green field. Okay, so the modes which are allowed now are, because we are considering for the moment the mode of 100 megahertz. So 100 megahertz, we have allowed 1 2 up to 5. Actually, it might be interesting if we check also what goes on with one of the modes being 6.
Profesor, këtu ku je?
Po,
2-0-ja, 3-0-ja, ti shpreh elektrik, apo jo?
po, Thujdhja Kristina si the?
Kjo mode 2-0. Noja 2, noja 0, 3-0.
Lejon gjitha patjetër, po, lejon.
Okay.
Lejon dhe gabim që nuk I ashtu që si përmendëm. Për shembull e bie njëra mund të jetë 0 dhe tjetra mund të jetë 1, 2, 3 prit. Okej, ke të drejtë, shumë e vërtetë. Biles mund të jetë 10. Let's add here 10, 6. Okay, so here we go. We get 10, another 10, another 10, and then we need. Yes, we need all zeros, right? Well, scanowujemy bogę szum, so this was a mistake maybe. Okay, not so many zeros, but we can put. I can have this one here. Okay, but you're right, Christina, that we needed these two. Okay, so we still have this. So you see here, you are right. So all the, if one of the components is 0, we can pick up these values here, and also, so since the A and B they are different, we are going to have. So we have quite a few, well, a lot of modes. In fact, yeah. So all the ones in green, they are allowed. And it looks like, so if we try to count those, we have quite a few. We have a lot of modes. So 04 apparently is not allowed, but 40 is allowed, 50 is allowed, 60 is allowed. But then here, this other respective or conjugate pair of numbers of m and n, they are not allowed. So now it remains to us to count them. But I believe 10 and 01, we have this here at the top. So actually these two, we have counted them before, but it's no problem. Okay, we can, if we want to correctly count them, we are going to be careful about those. Yeah, so this is how we can try. So if we approximately, here we have like, this is 5 plus 3, 8. 8, why do we have nothing here? Okay, 8 plus 3, 11, another 3, it's 14, 16 modes, plus 2, 18, 21, 21, plus 13, 34. So we have 34. A pair of these, this one and this one were on the top, so we get 32. We might have counted something wrong or something twice, but I don't think so. We have like 32 modes, which 32 modes of this 100 megahertz which can propagate. Okay, so let's write here. If we have 100 megahertz, we have 32 modes. Different can move through the tunnel. And what is the question is the following: which is the lowest mode which cannot propagate if the electromagnetic wave has a frequency of 100 megahertz? Let's try to identify now, or we can do it like this. We can say this is equal. We can easily notice this directly, but we just subtract this with -1. And we should be looking for the smallest positive number. How can we? So what is the smallest possible number? How can we put here a conditional formatting here? I saw something 0 point something, which was very conditional. Bottom above average more rules. Okay, apparently we can even set. So we want less than. Let's say 0.8. Okay, we want to make them green. So which one is? It should be a positive number and smaller than 0.8. So we said it's even smaller than 1. Negative. These are all negative numbers. Negative numbers. We are not interested in these. We want something higher because these negative numbers they are propagated. But now let's see. Oh, we are at the top. Apparently we could not distinguish. So we have here 1.88 actually. Okay. Anyways, the second trial, we can try again. Oh, here we have this now. Let's say the rules less than. We're looking for numbers which are less than 2. Let's say, okay, less than 2, but they should be positive. Less than 2. Okay, so apparently we notice this one, the 5.3. So this 5.3, it's a candidate answering our initial question. These are all negative. Okay, so it looks like the. Wait. These are pretty close. So it looks like the mode 5.3 is the first mode, which is just a little bit above. It's 1 megahertz above the frequency of the original wave. So this mode will be blocked. Okay. So apparently this cannot propagate. But was there any? No. Okay. Yeah. So this is how we can. And regarding the 80, so let's see here. How many modes can the 80 propagate? Conditional formatting. We want less than 80. Let's fill this with green. So it looks like we have quite a few. And as we said, this one is at the top. This one is also at the top. So we have approximately, we have 10 modes here, plus 3, 13, minus 2, 11, 11, 14, plus 2, 16, plus 2, 18, 21, 24, 27, and then here we have 27, 28, 29, 30, 31, 32. Oh, okay, we have 32. Also 100 had 32. Or maybe we counted them wrong. So these are, no, this is wrong. Because in green, we also have the 92. They should be less than 80. Then we have a mistake here. Conditional formatting, less than 80. Less than 80, okay. So less than 80, here we have 4 plus 2, 6 plus 2, 8, 10, 12, what is this? 12, this is 13 plus 2, 13 plus 2, 15, 15 plus what is the name? We have the 15 plus 13, we get 28. 28, 27, minus 2, 25, minus 1, 24. So apparently we get 24 modes here. This was a mistake. This is 24. Okay, so we get 24 propagating modes of 80, and we get 32 propagating modes of 100. Okay, and here I noticed one frequency at 80 megahertz, which is pretty close to, it's less than 1 megahertz above 80. So this is, we can say that the lowest mode, which cannot propagate in this tunnel for an initial wave of 80 megahertz, is the mode 6.2. Okay, because we have this 80.9, etc. Wait, so we are good here. A second. Okay, do you have any question regarding this type of problems? Okay, so we have the conditional formatting. Okay, that's good. So again, we can, we said that the lowest mode, so we made a mistake then here, not mistake, but this was apparently we're looking for the mode 6.2, 80.94. So this is 80.94 is the lowest mode which cannot propagate at the frequency of 80 megahertz. So we have to consider this one out of 24 allowed ones. This is just this value. No. This 80, yeah, this one is right at the boundary. Now, similar conditions we can also set. We can set again for the smaller than 100 and many more. Okay, so and let me think now. Click to reconnect. So what we can do then is the following. So we can have all of these frequencies. These are the cutoff frequencies. Let's see if we can do something. Now, these are the cutoff frequencies. They are moving up and down because we did not sort them. And let's try to sort them. So we copy these. You want to use the values, and we want to sort smallest to largest. Okay. So this is smallest to largest. We can call frequency 1. This is equal to these values. We can say figure 2 plot frequency 1. Okay, so here we have, of course, we have a lot of modes, but we can observe. Wait a second. So actually, at each data point here, we have the next jump in the frequency modes. Now, I believe, no, I was hoping to read the values specifically. Okay. Plot 1A, yeah. I think with Octave Online we cannot delve deeper into how to read the graph, but the values. So we take this away. Okay, so wait a second. Okay, so this is one way how we can think about how we can analyze the frequencies which can or cannot propagate through a certain rectangular waveguide as a function also of the input frequency. So now another question is the following: if we have 10 hertz, 10 megahertz, and by the way, we made this megahertz, not gigahertz. So this is megahertz now. So asking another question: if we have a frequency which is much lower frequency, which does not, or let's consider 5G, the 5G, which is the expected or already in use frequency of communication. Apparently, if someone wants to communicate with a cell phone or any device that operates at 5G, it looks like no mode can propagate. We have no numbers smaller than 5G. Okay, so then I'm wrong. I'm completely wrong. You should correct me, because these are megahertz. Okay, so again, if these were gigahertzes, okay, then the 5G, we would not be able to communicate with 5G. But of course, now consider the 5G and these. So these numbers, let's check actually for what size of the tunnel would make sense the discussion that we're just having right now regarding the 5G. So let's say that the tunnel, let's make this not 17 meters, but let's divide this one. Let's say that this is equal to 17, and let's divide this by 100. If we divide this one by 100, which means that this is 17 centimeters and B is 4.9 meters, this is an almost extreme case. But then, wait a second. This is the cutoff frequency. Okay. Actually, if this is the cutoff frequency, that means the 5G can easily pass through. Okay, then we have to think carefully about what we say. So we said that we will communicate it in 5G. 5G is 5,000 megahertz. 5,000 megahertz, and 5,000 megahertz is all larger than these values. So wait a second. So this mode, they can easily propagate. Okay, all the possible modes, not all the possible modes, whatever modes we see here. Wait a second, so this is 80. As long as these numbers are smaller than the frequency itself, they can all propagate. Okay, so the final verdict is here, that having this tunnel of 17 meters and 4.9 meters, the 5 gigahertz communication is possible. I mean, at least the wave can be propagated, okay, the boundary conditions will be satisfied, etc. Because for a moment I was confused using this. We have here these values, and now because as we said, so here we get we cannot say an infinite number of modes, but let's see, these don't seem to be increasing too fast, okay? So we have 300 megahertz compared to 5G, it's good. But what we can do is actually, let's see when the dimensions of the tunnel can be a barrier for the 5G communication. So let's assume here, we say 17, let's divide the meters by 100, let's make this centimeters. So we get 17 centimeters, then we get, yeah, everything is multiplied, and we say here 4.9 is equal divided by 100. First mode, I cannot see it, it barely moves. So, okay, so if these are in megahertz, let's turn this into gigahertz. Okay, so these are gigahertzes. Okay, so how can we remove this conditional formatting? We should do this conditional formatting. Clear rules. Okay, we cleared all the rules. So it looks like if we are going to communicate with 5 gigahertz for the 1-0 mode, this is the cutoff frequency. So this one is allowed, this is allowed, this is not allowed, okay? And so these are not allowed. Here we get a single allowed mode. So this is allowed, allowed. 5 gigahertz for 1 is allowed, and we can move ahead using the same automatic conditional formatting. Highlight rules less than 5, custom format, background color, going to make it red. Okay, okay. So the modes which can propagate 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 12, 13. We get 11 because this is a doublet. So we get 11 modes, 11 allowed modes. Wait a second. Okay, so this is, so for a tunnel or for a rectangular waveguide, which is 17 centimeters and 4.9 centimeters. Okay, so if you make a waveguide which is as big as a cell phone. So if we have this cell phone here, this is actually like 5 centimeters. This is around 17. So apparently, you make a aluminum foil in the shape of this. The cross-sectional area is this one. You extend this as much as you can, and then you can communicate through this 11 distinct mode composition of this 5 gigahertz. Okay. Okay. Do you have any question for what we discussed until now? Stop presenting. Okay. So this is the discussion regarding the allowed frequency modes. I believe you can see me here. And any other question that you might have? So we started this discussion considering which modes, how we can order them, or which one is the lowest order or highest order. Actually, we can rank them based on the smallest value or the largest value, or which value is right at the boundary between being allowed and not being allowed. Okay. Any other question? In fact, another important, and which can also be intuitive, another important aspect that we might need to keep in mind is how the parameters such as the phase velocity or the wavelength, how they depend or how they change as a function of the frequency, given a single cutoff frequency. So let's assume for a moment that we have the, let's say, we have beta. Okay, let's assume we have this equation. Beta is equal to beta 0 times the, so beta as a phase difference. This decreases when we go inside the waveguide, and this is equal to 1 minus the cutoff frequency divided by the frequency all squared. Okay. And this beta 0, this can be any phase frequency, what is this? Phase constant. That's wrong. This is not phase frequency. This is any phase constant, which can be in any wave. So if this one, let's assume that this is, for example, 2 pi over 3. Okay. So this is the phase constant. This is 2 pi over 3, and we want to check how this phase constant changes as a function of the frequency, as you said. But let's assume that we want to consider this one, let the cutoff frequency be 10, and we want to check this as a function of f. Okay, so this is how we can, at least this is what we have to do if you want to draw relationships, or relationships as a function of the important parameters of a wave, how they increase or decrease inside the waveguide. And now the similar consideration can also be done for when we consider the dispersion relationships, which show how the omega change as a function of k. But we're going to talk about this one later. So we're talking about how the angular frequency changes as a function of phase constant. Now probably, okay, so we can draw graphs of these. So far, do we have any question? So this is equal to space. So let's have a look here. X is equal to length space. We want to generate numbers from, let's say here we have from 10. So the cutoff frequency is higher. Let's assume that this is from 9 to 12. Okay, so this produces numbers which are from 9 to 12. That's good, and we call this one x. So if this is x, then we say beta 0. This is equal to 2 times pi divided by 3. Okay, how is pi here? Pi. Okay, apparently this is pi. So beta 0 is a little pi here. So this is the beta 0. Then we have to figure out how the beta, it will be 1 minus 10 over f, but it's all squared. So this is, you can have a ff, this is equal to the square root of 1 minus 10 times 10, because this is 10 squared, divided by x divided by x. Okay. We cannot do this operator. So we can say the following actually. We can say xx is equal to x times x. This is a vector. Okay, so we got this. And we get, this is, xx is this parameter. Okay. Then we need to write a ff. This is going to be equal to the square root of 1 minus 100 divided by xx. Okay, so we have another problem that not, wait a second, so this is, the issue is that xx, it includes also values, maybe, but this should take the square root of, maybe it's a problem, it cannot calculate this, of course it can. And let's do this one, fff, which is equal to 100 divided by xx. we do this one. 1 divided by xx times 100. Okay, we found it. Okay, so apparently, let's see, we wrote this important factor is FFF. So this is, then we have 1 minus FFF square root. So we need 1 minus FF, 3 f's, function, divided by the square root. So we say that beta is equal to beta 0 times the square root of 1 minus square root 1 minus, yeah. Okay. Okay, so here, this is what we observe. So apparently, this is how the beta is going to change as a function of the frequency. But this is as a function of the frequency, assuming that we have a fixed mode, because this fixed mode, it has a cutoff frequency at 10. Now, this 10 is, since we are going to divide here the cutoff frequency with the frequency itself, if they are both megahertzes, they are going to cancel out each other. If they are both gigahertzes, they are going to cancel out each other. And this, apparently, this is what we observe for the beta as a function of the frequency, which means that beta is along the y-axis. So beta, it is increasing. Yes, it's increasing as a function. The phase constant, it is increasing as a function of frequency. Okay. So similarly, we can also draw the graphs of how the phase velocity changes as a function of the as a function of frequency and many more. Now, if you like, we can have a short break here. Oh, wait a second. So